All right, good morning. I'm Amy Flicksteiner. This is Elementary Algebra, and we are going to be working on section 2.7 today. This is inequalities. So to begin with, we're going to talk about some of the basic inequalities and what those look like. So inequalities are when things are not equal. It could be that we're talking about this inequality symbol, which is read out as is less than. The second one I'm going to show you is that same symbol, but with a line underneath. That means is less than or equal to. So this includes a possibility that it could be equal to that number. There is also greater than. And similarly is greater than or equal to. The one we most frequently forget is not equal. Inequality statements can be true, such as something like 4 is greater than 0. This is a true statement. They can also be false. And a false statement would look something like -10 is bigger than -4. That's not true. -10 is smaller than -4. So -10 is greater than -4 would be a false statement. They can also be neither. And neither means we have some variability in it. Neither generally looks something like x is less than or equal to, I don't know, 1. Right? I don't know if x is less than or equal to 1 until I know what values I'm putting in for x. This leads us to a linear equation in one variable. Linear equations in one variable can look like, what did the textbook have? Oh, okay. Linear equations in one variable can look something like a is greater than 4, or a is less than -2. 2x minus 7 is greater than or equal to 0. 1/5 x plus 3 is less than or equal to 0. All of these are inequalities in a singular variable. Okay? We can test, what I have is -3. A solution to the inequality, 4x plus 5 is less than or equal to a -6. How will I know if that is a solution? I'm simply going to put the -3 in for the x. So 4 times -3 plus 5, is that less than or equal to a -6? This should be somewhat familiar to you as we have checked these solutions before. So I have -12 plus 5, which is a -7. Is that less than or equal to a -6? This is true. -7 is smaller than -6. So if I need to check the validity of a statement, I can put it in and see if it's true or false. That is the way to do it. Okay. The second piece of this particular section is that we want you to be able to graph solution sets and to use interval notation. When we have a solution to an inequality, the solution to an inequality is not a singular number. It is an inequality statement. Oops, I forgot my N. And it will generally look something like x is less than 4. This is said as x is less than 4. And we use something known as set builder notation. Which puts in a curly bracket and the letter x such that your x has to be less than 4. So basically this calls out the variable as being x. This straight line says such that x is less than 4. This is what that answer or solution set looks like in a set builder notation. We also graph the inequality. And when we graph it for a singular variable, we will graph it on the number line. That means I will need a number line. I generally put in a 0. And then for x less than 4, we need to be able to go to 4. Not every hash mark on the number line will be listed. That's fine. 4 would be there. -4 would be there. All right. When we graph this on the number line, there is 2 methods. Four, 5, 6, 7, 8. -4. There we go. Both of these methods will portray the same information. They're just preferences, really. So whichever one you like. All right. So the idea here is that x's have to be less than -4. You may be familiar with the first method, which says we're going to use an open circle. An open circle indicates that we were not equal. It had to be strictly less than 4. It could not be equal to 4. And if we look at the numbers which must be strictly less than 4, I prefer to test a single number. In this case, I'm going to test 0. And I'm going to ask, is 0 less than 4? If it is true, then you shade in that side. Okay, I'm putting the arrow because it does keep going. It keeps on going. Any number less than 4. So it doesn't just stop here at this negative. I need that arrow to include all numbers less than 4. Okay, this would be the first graph with the open circle and the arrow. The method number 2 would not use an open circle, but rather would use a parentheses. And we're still going to be shading in the direction of 0. So that part remains the same. And we're still going to use the arrow to say that we include all the numbers less than 4. Now, some people really like the circles, some people really like the parentheses. Both are okay. I used the open circle for a very long time. I have switched to the parentheses these days because of the third way that we would indicate a solution, and that is what's known as interval notation. Interval notation is a mathematical shorthand that doesn't rely on set builder and it doesn't rely on a graph because both of these can be cumbersome. Set builder notation relies on a very specific set of notations. That's why it's called notation. All right, so here's what happens. Do you see how this is an open circle at a 4? And see how it's the end. On our graph, it's the furthest to the right. So when I write this in interval notation, I'm going to use that parentheses, the same one I used in this method, because this parentheses indicates an open circle. It is the same as the open circle. And I'm going to put a 4 there. Okay? So it comes all the way up to, but does not include the 4. So rounded bracket, because it does not include the 4. Where did it start? If we're reading from left to right, we got to figure out where it started. Which number did it start at being less than 4? And the fact is, it didn't start at any specific number. It started way over here in the negatives someplace. Which negative number? We don't know. Because whatever one I start at, I could go even further. So we're going to use the concept here of infinity, only we're going to stick a negative on it. We're going to say it started somewhere over here in the negative infinities, meaning the really, really small numbers to the left. And in order to show that it's to the left, I'm going to put the negative on it. And now, because it's not an exact number, I can't jump on a negative 1 million. That's not where it starts, because it could have been a negative 2 million. Because this is not an exact number, I'm going to use the rounded parentheses on that one too. Okay, so now I have the 3 different methods of writing a solution here. I have what's known as the set builder notation, which looks like curly brackets, x such that x is less than 4. I have that graph on a number line, which could be an open circle with an arrow, or you could use parentheses or rounded bracket with the arrow to the left because it's less than. And lastly, we have the option of interval notation, which is really short and sweet, but involves you knowing what the different symbols are. That the brackets, or I'm sorry, that the parentheses mean it wasn't exact. That negative infinity means we're coming way, way, way from some negative number, I don't know where. And that it goes up to 4, but this says it does not include or cannot be equal to 4. Okay. All right, so now what I want to do is I want to practice with you solving some inequalities. And then we're going to give that solution in all 3 of the manners that are required here. All right, so when you solve an inequality, what you're being asked to do is to find all the solutions. Or the solution set for the variable. That make that inequality true. What makes that inequality true? Sometimes inequalities will be equivalent, meaning the same set. Ooh, that was my stomach. Did you hear that? Equivalent inequalities have the same solution set. All right. So I have 4 or 5 examples here. This could be a sort of a longish section. I'll try to go quick but thorough, right? You can always go to double speed if you need. All right, so let's try the first example. We'll try example 1, and I'm going to have us solve here a pretty beginner one, right? So we'll do x minus 5, and we'll say that's less than or equal to 3. Now, I know this looks a little bit intimidating, but really to solve it, you're going to do very much the same thing as you would do with an equation. We're going to think of this as x minus 5 is equal to 3. We just want to solve it like an equation. In our head, we want to make that substitution. So we are going to add 5 to both the left and right sides. And this gives us x is equal to 8. And so now we just want to replace that inequality symbol. So our x values would be less than or equal to 8. There's 3 different ways to write this solution. The first is in our set builder notation. That would be the set containing x such that all of the x values are less than or equal to 8. And that's fine. That's what it looks like in set builder notation. They could also ask you to graph this. On a number line, I usually put in my 0, and then it's okay if I don't have the availability to get all the way up to 8. I'm just going to count by 2s, 2, 4, 6, 8. And then I just have to make sure that on the other side, I'm also skip counting by 2. I don't want to count by 1s on this side and 5s on that side. That makes things a little crazy. But I just want to skip count by the same amount. It's less than or equal to the 8. Since it's less than or equal to, I would use a closed circle because it can land on 8. And since it's less than, when I test a 0, 0 is less than or equal to 8, that tells me which direction I would shade in. And since it will keep going, I would put on my arrow, right? Now, if I'm doing this using the other method, let's say that's a -4 and that's an 8. I can't use the rounded bracket here because the rounded bracket says it won't land on 8 exactly. This particular set says it can be 8. So if I'm using the other one, then I'm using the squared off bracket. And I'm still saying, okay, yep, it works in the same direction as the 0. The 0 is less than 8, 10 is not, so I want to go towards the 0. So the graph could be either one of these two. And I believe when you're working on WebAssign, you do have the option to use either one of those. All right. The last option is the interval notation. And the interval notation would be, once again, coming from over here. That arrow tells me I'm way in the negative infinities. And I'm going up to the 8. Now, the negative infinity is always going to be not an exact number. So infinity is always going to be a rounded parentheses. The 8, however, is spot on. That is a hard stop. It can be 8. So in interval notation, it will be a rounded parentheses, negative infinity, comma 8, hard stop. Okay? All right, so these are the 3 possible ways of answering this particular question. Just to be clear, you don't need both graphs. It's one or the other. You don't need both of them. I'm just showing you the 2 methods. Method 1 would be a closed-in circle. Method 2 would be a square bracket. My preference is for the square bracket because it transfers into the interval notation. Right? Okay, let's try a second example. Our second example is we're going to solve a negative 3/5 x is greater than or equal to 10. Okay, so all of our rules are pretty much the same. We're just going to ignore this and replace it like it's an equal sign. I'm not going to actually do it like I did for this one. I'm just going to do it in my head, okay? What I need to remember here, though, is that all of the rules of equality stand except for the multiplicative property of equality. This is a big deal, and it switches up your answer. So while I'm going to do both sides of this equation, I'm going to multiply by a 5. I've got a denominator, so I am going to multiply both sides of this equation by 5. That's going to give me a negative 15 over 5, which will just be a negative 3x is greater than or equal to 50. So I've got a negative 3x is greater than or equal to a 50. The 5's and the 5's technically cancel, leaving me with a negative 3x, and 5 times 10 is 50. Notice my C value. What I'm multiplying by is bigger than 0. So my inequality sign will stay the same. Okay? My inequality sign does not change. However, my next step is going to be to divide both sides of these by a negative 3. This triggers an issue. Do I have that? Oh, yep, no. This triggers an issue with the inequality. So when I multiply or divide, because division is multiplication by the reciprocal, so when I multiply or divide by a negative number, that switches your sign. So watch out for that, right? Sign switch. The inequality sign switch. So notice here the inequality sign was greater than or equal to. When I divide by a negative number, it switches. If I were multiplying by a negative number, it would also switch. But it's only when you multiply or divide by that negative number, right? So if I had to write this answer in Set Builder, it would look like x such that x is less than or equal to a negative 50 over 3. And no, I am not going to change that into a mixed number, and I am certainly not going to change it into a decimal. We leave these in fraction form. If I'm doing the graph, I'm going to find my 0, and I'm going to approximate where a negative 50 over 3 is. Negative 50 over 3 is about negative 16 2/3. So what I'm going to do is that's an odd one. Negative 16 2/3. 5, 10, I'm going to say this is 15. There's 5. 10, 15, 20, there's 25. So a negative 5, 15. A negative 16 2/3 is going to be somewhere around here. Right? And it's less than or equal to. And I've got to go, 0 is not less than that, so I've got to go this way. Okay, so we're going to do this. And we're going to fill it in this way. And I've got the relative position okay. So I'm just going to call that negative 50 over 3 so that it's marked. I've done my square bracket. So now in my interval notation, that's going to look like negative infinity again. That's always a round bracket, negative infinity. And then I need 50 over 3, negative with a hard stop because of the equal to. And there's my 3 ways of writing this out in Set Builder notation. 2 there. Let's do one more. All right, let's do one more. We'll make it a little bit harder. Okay, let's see. What can we do? Let's do 3 is less than a negative, 4x plus 11. So let's try that one. 3 is less than a negative 4x plus 11. I'm going to treat this sign just as an equal sign and solve this inequality as I would an equation. Meaning I'm going to subtract 11 from both sides. That gives me a negative 8 is less than a negative 4x. And then I'm going to divide both sides by a negative 4. Note that I am again dividing by a negative. That is going to cause this sign to switch. So that's going to give me 2, and on this side I'm going to have x. Now, to write this, this would be x is less than 2. Right? 2 is bigger than x, so x is less than 2. That inverts that sign as well. So our set builder notation would look like the set containing x such that x is less than 2. On a number line, we would have a 0, and I'm just going to do a 2 there. That 2 would be an open circle, and since 0 is less than 2, I need to do an open circle at 2 and go in the direction. This is less than again. Man. Which means my interval notation would look like negative infinity to 2, and again the parentheses. The 3 different ways of writing that solution. Okay, do we want to try a really sort of involved one maybe? Should I do one more? Let's do one more where the solving is a little bit, and then there's still a couple of goals here for this particular unit, but let's try an example here. What do I got? I've got 4 times x minus 2 is less than, I guess 2x plus 1 plus x. Okay. So this one's a little bit harder for the solving bit, right? All right, so on the left side, I'm going to distribute. That's going to give me 4x minus 8. Is less than, that's going to stay the same. On the right side, I'm going to distribute 2x plus 2 plus an x. Okay, on my right side, I can combine like terms. On the left side, I can't do anything. Now I have x's on both sides. I'm going to subtract 3x from both sides to get them all over on one side. That leaves me with an x minus 8. 3x, or 4x minus 3x is 1x, less than, that's going to be a 2. Notice I subtracted 3x. That's a subtraction, not a division or multiplication. Subtraction does not flip this sign. It's only if you're multiplying or dividing, not if you're adding or subtracting. So now I'm going to add 8, and I'm going to get x is less than 10. So this would be in set builder, the set containing x such that x is less than 10. If I was graphing this, I would have a 0, I would have a 10. Is 0 less than 10? Yep, so I want to shade that. These are all less than. Okay, so this would be, since it's not equal to, this would be the rounded bracket, and I'm going in this direction. So that's what it would look like, making sure to put my arrow on. And then in interval notation, we're starting at some negative infinity, and we're going up to 10, but we cannot be 10, so rounded bracket. These are the three different ways to write the solution, using set builder, graphing it, and using interval notation. Okay, I'm going to take a break for a minute. Okay, so I did want to do one other example on this, just because I feel like we got gypped out a little bit, just always using the less than. So I'm going to do one more example that I found. This one comes from number 60, in the problem set. So this is 3x minus 10 over 5. Right? Yeah. Is less than or equal to x plus 4. Okay. So I'm going to practice some of the skills from solving and make sure you see a slightly different version here. So do you see how you have the denominator of 5? I'm going to go ahead and eliminate that denominator by multiplying both sides of this equation by 5. When we do that, on the left side, the 5's here will cancel. This will be 5 over 1, and we're dividing by 5, so 5 divided by 5 is going to leave us with a 1 and a 3x minus 10. Okay, on the right side, that 5 is not eliminated. It now needs to be distributed to both the x and to the 4. So that's going to leave us with 5x plus 20. Right? We now have x's on both sides. We can subtract the 5x from both sides. That's going to leave us with a negative number. Or we can subtract 3x from both sides. It won't matter. Either one will do. So I'm going to subtract 3x because I like to avoid negatives whenever possible. And that's going to leave me with a negative 10 is less than or equal to 2x plus 20. Now I'm going to subtract 20 from both sides in order to isolate the x. That gives me a negative 30 less than or equal to 2x. And to further isolate the x, we will divide by 2. Negative 15 is less than or equal to x. To visualize it so that the variable is first, this is the same as x is greater than or equal to a negative 15. Now, this is my solution. I can write that solution in set builder notation, negative 15. I can graph that solution on a number line, negative 15, and I need it to be greater than or equal to. Greater than or equal to means the 0 will work. 0 is bigger than or equal to a negative 15. That is true. So I want to go in the direction of the 0. Since this is an equal to, that's a square or hard bracket. And then I can go everything above. What that means in interval notation is that it will start at a negative 15. And it will continue on infinitely until every number has been exhausted. I don't know what number that will be, so I'm going to use the infinity symbol. And again here, since infinity is not an exact answer, I will use the rounded bracket because it's not one single number I can give you. Infinity is a concept, meaning it's the idea that the numbers go on and that there is no one largest number or one smallest number. Okay? All right, so what do we do from here? Well, you would think this would be it, except we're going to kick it up one more notch. We're going to talk about compounded inequalities. Specifically, we're going to talk about the compounded inequality with the word and. And that looks like two inequalities put together. So, what if x was less than 3, but it was bigger than or equal to a negative 1. This is known as a compounded inequality. It means that x will be greater than or equal to a negative 1, and x has to be less than 3. Right? This is two statements combined into one. It's why it's called a compound inequality, because it is two compounded together. They are held together by the word and, which is an English compound. Right? In English, we call and a compound. Right? Okay, so what does this look like? Well, if we're doing a set builder, it's just x such that negative 1 is less than or equal to x, which is less than 3. We like set builder because it's just really straightforward. Most of the time, it's exactly what works. On a graph, we actually have to consider, first of all, the important numbers. I'm going to put my 0 in on this one, but I also need to have a positive 3 and a negative 1. Notice I'm not putting in all the other numbers. You can if you want. But those are the two numbers that I need because they're in my compounded inequality. At negative 1, we have a closed circle or a bracket, and x is at 3, an open circle or parentheses. It just depends. So what we want to do is I'm going to divide this graph into 3 sections. So if I'm here at negative 2, is negative 2 bigger than a negative 1? Is that a yes or a no? Negative 2, if I put that in for the x, is that bigger than a negative 1? Nope. What if I do a 0? Is 0 bigger than negative 1? Yes, it is. What if I did something over here in this section of the graph? Let's say a 5. It's not on the graph, but it would be over here, right? So what if I pick a number over here like a 5? Is 5 bigger than negative 1? Sure is. What if I checked the negative 3 section? Is negative 2 smaller than negative 3? It's a yepers. What about a 0? Is 0 smaller than a negative 3? That is a yes. What about a 5? Is a 5 bigger than a negative? 5 smaller than a negative 3? That's a no. Right? It's not going to work over here. So now, looking at this, I want to know for what set of values is the x going to be bigger than a negative 1 and less than 3? Well, that's going to be the part where you have 2 yeses, or the part here in the center. So when we do this on a graph, we're looking for these numbers that are between. And when we put in the notations on the graph, we now know that for negative 1, it's equal to, so we need the hard bracket, but we're going to face it towards the 3 because we know it's these inside of here that work. And we know the 3 should be a rounded bracket. It can't be 3 exactly, right? So I'm going to use a rounded bracket, and I'm going to face the negative 1. And then all of these numbers in between will work. So on the graph, it will look like a square bracket, a rounded bracket, and everything in between for this one because of the greater than or equal to and the less than. What does it look like in interval notation? Interval notation is taken almost exactly from this graph. So it will be a square bracket starting at negative 1 and going up to 3 where it is not exact. No infinities here because we have a finite set of numbers that work. So it's just going to be within this set. All right, let's try some examples. Okay, let's try 3 is less than x plus 11, which is less than or equal to, let's try 13. Okay, so we need to split this into 2 parts. The first part will go all the way up to that inequality sign. So that first part will look like 3 is less than x plus 11. And then we're going to work on the second part, which is going to start at that inequality and go all the way to the end. Ouch. Right, we're going to solve each of these inequalities. So I'm going to subtract 11 from both sides. Then I'm going to turn it around so my variable comes first. I know x will need to be greater than -8. And then on my second inequality, I'm going to subtract 11 again. And that's going to give me x is less than or equal to 2, which is already variable first, so I'm good. Now, in the set builder notation, I put them back together. This is a set containing x such that, and I'll look at this row, -8 is less than x, which is less than or equal to 2. If I'm going to graph this one, let's see, I need a 0, I need a 2, and I need a -8. Then I can choose, let's choose a 5, let's choose the 0, and let's choose a -10. Okay. If I'm looking at, let's see, -10, 0, 5. Okay, so if I'm looking at the one I did here in yellow, is -10 bigger than -8? No, -10 is not, so I will not be graphing on this side. Is 0 bigger than -8? Yes, indeed it is. Is 5 bigger than -8? Yes, indeed it is. Now, if I look at what I did in pink, is -10 less than or equal to a 2? Yep, indeed. Is 0 less than or equal to a 2? Yep, indeed. Is 5? Nope, it's not. So the only place where they both worked was the 0. And the 0 is standing in for all the numbers between -8 and 2, which means, again, I'm just going into this section. Now, when I go to graph it, my -8 is one of my numbers here, and it's greater than but not equal to. So I'll need the rounded parentheses there because it's not equal to. The 2 is equal to, so I can use the square brackets on that. And we've indicated that all numbers, our tests show all numbers in between will work. So I want the graph this time to go from -8 to 2, where -8 is rounded and 2 is the square bracket, which means my interval will go from -8 rounded to 2 with a square bracket. Okay, that's what it looks like in interval notation. They do get harder, but that's the base. Okay. Okay. The last bit in 2.7 is some inequality applications. What I have here are some of the different translations and some of the different English settings, if you see A does not exceed B, then the expectation is that you can translate that to A is less than or equal to B. If you see A will exceed B, that means A will be bigger than B. Surpasses means A is bigger than B. Is no more than means it can be equal, but other than that will be less. So A is less than or equal to B. Is at least B is a way of saying that A is the starting point, but everything bigger works. So A is at least B means A is bigger than or equal to B. A is at most B means B is the limit and A will be less than or equal to B. A is between B and C means that C would be less than A, would be less than B, or the other way around, B would be less than A, which would be less than C. A is not less than B means it could be greater than and it could be equal to. A is not equal to B means A is not equal to B. Can't be either. It's either going to be bigger or it's going to be less. It's just not going to be equal. So what we're asking you to do here is to set up some equations and solve them. Do I have 2 pages here or just one? Yeah, no, just one. All right, so if a student has scores of 68%, 67%, and 72% on 3 exams, what percent score does he need on the last to earn a grade of at least, of no than a C? I think I meant no more than. No more than. I think I forgot the word more. All right, so student scores a 68, a 67, and a 72% on 3 exams. What percent score does he need on the last test to earn a grade of no more than a C? No more than a C. I know. I think I want more. No more of more than a C. Yeah, we want more than a C. Right? Because more than a C would mean that the grade is bigger than or equal to, no, more than, of more than, so greater than 70. So if he wants a grade of greater than 70, what does he need on the last test? Well, assuming that the test is an average, the average would be 68 plus 67 plus 72 plus some 4th score we do not know. All of this divided by 4. Because that's how you find an average, right? You add them all up and divide by 4. The problem here is we do not know that 4th test. So 68 plus 67 plus 72 plus some value of x, all of that over 4, would have to be greater than 70. So when I put this together, what do I do to solve this? Well, to solve this, we'll take a few steps. My first step is going to be to multiply both sides of this inequality by 4. On the left side, this is just going to give me 68 plus 67 plus 72 plus x has now got to equal 280. Right? 4 times 70 is 280. And on the other side, when I've added them, well, I'm sorry, when I've multiplied by 4, this 4 that I'm multiplying by will cancel with the 4 in the denominator. So 67 plus 68 plus 72 . 68 plus 67 plus 72 is 207 plus x has to equal 280. Oh, it's not equal though, is it? It's greater than. That's what I want. Greater than. Now I'm going to subtract 207 from both sides. So what does this tell us? This tells us that the fourth test must have a score of more than 73. If they do not score at least a 73 on this test, they will not have an overall average of greater than 70. Right? Okay. 4 more than 3 times a number is no more than negative 15. Determine the solution set. 4 more than, okay, so that's 4 more than, that's plus 3 times a number is no more than, is not more than, is no more than. If it's no more than, it has to be less than. Does it have to be equal? If it's not more than, can it be equal? Less than or equal to negative 15. Okay, so this gives me the inequality. 4 plus 3n is less than or equal to a negative 15. I just need to determine the solution set. So I'm going to subtract 4 from both sides. 3n is less than or equal to a negative 19. I'm going to divide both sides by 3 to get the n alone. N is less than or equal to a negative 19 thirds. So the solution set is a set of n such that those n are less than or equal to a negative 19 thirds. That's it. That's my solution set. In set builder notation. If they just want the solution set, they may just want this piece. N is less than or equal to negative 19 thirds. Okay. All right, a new video application has signed up 125,000 users. If an average of 12,000 people are signing up per day, how many days until the company surpasses its goal of 1 million users? So they want to surpass 1 million users. So we want to know when users are greater than 1 million. Okay, what do we know currently? We know currently there are 125,000 users and they're getting 12,000 people per day. So we're also getting 12,000 each day. This 1 million should be made up of 2 different parts. We should have the 125,000, and we're going to add to that 12,000 people each day. Until our users are over 1 million. So if I'm writing this as an inequality, I'm going to do 5,000 plus 12,000 a day. So I'm going to put a D in there for each day. Has to be greater than 100 or 1 million. So how many days do I need? Yeah, that's good because my days are, there we go. So now I'm going to subtract 125,000 from both sides. And that's going to give me 12,000 times the number of days is greater than, oh, that's not going to be, minus 125,000. And I get 875,000, which I will now need to divide by the 12,000. and I get my days has to be greater than 72.916, or technically 73, right? Our days need to be greater than 72.9, so our days need to be, yeah, that's all right. I can leave it as 72.9. You can't really have 72.91 days, but if I do 73 days, then it would have to be greater than or equal to, because we could be 73 days. So we need 72.91 days. So when will they have hit 1 million? Well, if they need greater than 70, okay, so I would say at 73 days out, they should have 1 million. Yeah. Okay. Whew, this was a long one. All right. As I've said before, if you have any questions, please don't hesitate to reach out to me. The Math Center is also available for assistance. They are great. Julia has taught this class before, and she's whose videos you're looking at in some of the other options. So, all right. Thank y'all.